In a mass spring system, oscillation occurs when a mass repeatedly moves back and forth about a fixed equilibrium position. The equilibrium position is the central position around which the mass oscillates. In the diagram, this position is marked as nend. The mass can move to the left of this position, pass through the center, move to the right, and then return to the center again. The sequence can therefore be described as left, center, right, center, left, and then the motion repeats. This repeated back and forth movement is called oscillation. The equilibrium position is extremely important because it provides the reference point from which displacement is measured. When we say that the mass has a displacement of ninths, we mean that it is displaced to one side of equilibrium, usually chosen as the positive direction. When we say its displacement is 9, it means that the mass is on the opposite side of equilibrium. In the diagram, the right extreme position is labeled 9, while the left extreme position is labeled 9. Here, 9 represents the amplitude, which is the maximum displacement of the mass from its equilibrium position. Imagine that the mass is initially at the equilibrium position in the center. If we pull the mass towards the right and hold it there, the spring becomes stretched. When we release the mass, the spring produces a restoring force that acts towards the left, trying to bring the mass back towards its equilibrium position. The mass therefore begins to accelerate towards the center. As it moves towards equilibrium, its velocity increases. When it reaches the equilibrium position, it does not necessarily stop. Instead, it passes through the center because it has gained velocity while moving towards equilibrium. After passing through the equilibrium position, the mass continues towards the left side. The spring is now deformed in the opposite direction, so the restoring force also changes direction. The restoring force now acts towards the right, again towards the equilibrium position. The mass therefore slows down as it moves towards the left extreme position. Eventually, at the left extreme position, the mass reaches its maximum negative displacement and momentarily stops before reversing direction. The mass then begins moving from the left extreme position back towards the center. The restoring force acts towards the right, so the mass accelerates towards equilibrium. As it approaches the center, its speed increases. It passes through the equilibrium position again and continues towards the right side. Eventually, it reaches the right extreme position, where its velocity becomes 0 for an instant before the entire process starts again. This repeated cycle produces the oscillation shown in the diagram. The equilibrium position can be understood in terms of forces. At equilibrium, the forces acting on the mass balance each other, so the resultant force is 0. In the simple horizontal spring system shown in the diagram, if there is an applied force or another opposing force, the equilibrium position is the position where these forces are equal in magnitude and opposite in direction. For example, if one force nth acts towards the right and another force nth acts towards the left, then at equilibrium nin. Because the forces are equal and opposite, the resultant force is 0. A 0 resultant force at equilibrium means that the acceleration is 0 at that exact position, because Newton's second law tells us that nin. If the resultant force is 0, then the acceleration is also 0. However, this does not mean that the mass must have 0 velocity at equilibrium. This is a very important point in oscillatory motion. When the mass passes through equilibrium during an oscillation, it can have a significant velocity, and in ideal simple harmonic motion, its speed is actually maximum at equilibrium. So, equilibrium means 0 resultant force and 0 acceleration at that instant, not necessarily 0 velocity. Now consider the two extreme positions. At the right extreme position, the displacement is 9, meaning the mass is at its maximum positive displacement from equilibrium. At this instant, the mass has reached the furthest point on the right, and its velocity is 0 for an instant. The restoring force is directed towards the center. Similarly, at the left extreme position, the displacement is 9, the velocity is again 0 for an instant, and the restoring force acts towards the center, this time towards the right. The fact that the restoring force always acts towards equilibrium is what allows the system to oscillate. If the mass is displaced to the right, the restoring force acts to the left. If the mass is displaced to the left, the restoring force acts to the right. Therefore, the restoring force always opposes the displacement. This can be represented mathematically for an ideal spring by Hooke's law, N. The spring constant is represented by N, while N represents displacement from equilibrium. The negative sign tells us that the spring force is in the opposite direction to the displacement. For simple harmonic motion, this restoring force leads directly to the important acceleration relationship. Using Newton's second law, 9, and the spring equation 9, we obtain. Dividing both sides by the mass gives 9. This has the same form as the SHM equation. Therefore, for an ideal mass spring oscillator, 9. This means that the acceleration of the mass is directly proportional to its displacement from equilibrium and is always directed towards equilibrium. The diagram shows the mass moving between 9 and N. These two positions represent the maximum limits of the oscillation. The distance between the two extreme positions is nath. If the amplitude is inch meters, for example, the mass moves a maximum of inch meters from equilibrium in either direction, and the total distance between the extreme positions is inch meters. Remember that amplitude is measured from equilibrium to one extreme, not from one extreme to the other. Displacement is constantly changing during the oscillation. At the right extreme, the displacement is. As the mass moves towards the center, the displacement decreases towards 0. At equilibrium, 9. After passing through the center, the displacement becomes negative. It reaches 9 at the left extreme, then increases back towards 0 as the mass returns to the center. This continuous change in displacement is one of the defining features of oscillatory motion. The velocity also changes throughout the motion. At either extreme position, the velocity is 0 because the mass must reverse its direction. As the mass moves towards equilibrium, its speed increases. At equilibrium, the speed is maximum in ideal, simple harmonic motion. As the mass moves away from equilibrium towards the opposite extreme, its speed decreases. Eventually, it becomes 0 again at the extreme position. Therefore, the object continuously exchanges speed for displacement and displacement for speed throughout the oscillation. The acceleration follows a different pattern. In simple harmonic motion, the magnitude of acceleration is greatest when the displacement is greatest, which occurs at the extreme positions. At the right extreme, the acceleration is directed left towards equilibrium. At the left extreme, the acceleration is directed right towards equilibrium. At equilibrium, the displacement is 0, so the acceleration is also 0. Therefore, the three key positions can be remembered very clearly. At an extreme position, displacement is maximum, velocity is 0, and acceleration is maximum. At equilibrium, displacement is 0, acceleration is 0, and velocity is maximum. The sequence shown at the bottom of the diagram, displacement, restoring force, movement towards equilibrium, passage through the center, movement towards the opposite side, and repetition, represents the cause and effect process behind the oscillation. First, the mass is displaced from equilibrium. This displacement causes a restoring force to act. The restoring force accelerates the mass back towards equilibrium. The mass passes through the center because it has velocity. It continues to the opposite side, where the restoring force changes direction. The mass slows down, reaches the opposite extreme, reverses direction, and returns again. This process repeats continuously. One complete oscillation occurs when the mass returns to its original position with the same direction of motion. For example, if the mass starts at the right extreme position, moves through the center to the left extreme, and then returns through the center to the right extreme again, one complete oscillation has occurred. The time required for one complete oscillation is called the period, represented by EN. The number of complete oscillations per second is called frequency, represented by EN, and the relationship between them is EN. For an ideal mass spring system, the period is given by EN. This equation tells us that the mass and spring constant affect how quickly the system oscillates. Increasing the mass makes the oscillator slower and increases its period. Increasing the spring constant makes the spring stiffer, allowing it to provide a stronger restoring force for a given displacement, so the oscillator moves more rapidly and has a shorter period. The amplitude does not appear in the ideal spring mass period equation. Therefore, for an ideal spring obeying Hooke's law, changing the amplitude does not change the period, as long as the spring remains within its appropriate elastic range and the ideal SHM assumptions remain valid. A larger amplitude does, however, mean that the mass reaches a greater maximum displacement, greater maximum speed, and greater maximum acceleration. The equilibrium position can also be understood as a balance point. Imagine pushing the mass slightly to one side. Once the external displacement is created, the spring force no longer balances in the same way, so a resultant restoring force appears. This resultant force produces acceleration towards equilibrium. As the mass approaches equilibrium, the restoring force becomes smaller. At equilibrium, the relevant forces balance, and the resultant force becomes zero. But because the mass is moving, it can pass through the equilibrium point and continue to the other side. It is important to understand that the equilibrium position is not necessarily the same as the position where the spring is completely unstretched in every possible spring system. For a horizontal spring with no other horizontal forces, equilibrium may correspond to the spring's natural length. But if an additional constant force is present, such as an applied force or another force acting on the mass, the equilibrium position can be shifted. The important definition is that equilibrium is the position where the resultant force on the mass is zero. For a vertical spring, this idea becomes even more important. When a mass hangs from a vertical spring, gravity acts downward while the spring force acts upward. The equilibrium position occurs where the upward spring force balances the downward weight, therefore at equilibrium 9, and the resultant force is 0. If the mass is then displaced slightly above or below this equilibrium position, a restoring force develops and the mass can oscillate about the new equilibrium position. This is why the equilibrium position should always be identified before analyzing an oscillating system. Once the equilibrium position is known, displacement can be measured from it, the direction of the restoring force can be determined, and the extreme positions can be identified. In an SHM problem, the equation 9 always uses displacement measured from the equilibrium position, not from an arbitrary point. The most important idea from this diagram is therefore that the equilibrium position is the central reference position about which the mass oscillates. When the mass is displaced from equilibrium, a restoring force acts to bring it back. The mass moves towards the center, passes through equilibrium, continues to the opposite side because of its velocity, and is then pulled back again. At the extreme positions, the velocity becomes zero and the restoring effect is strongest. At equilibrium, the resultant force and acceleration are zero, while the velocity is maximum in ideal SHM. This continuous interaction between displacement, restoring force, acceleration, velocity, and equilibrium position produces the characteristic back-and-forth motion of a mass spring oscillator.